But if not, anyways, I think I'm going to get started. So before I get started, welcome to 15251 Weekly Review. Before I get started, I kind of want to just like quickly motivate why we even care about randomized algorithms in the first place and why we're studying this topic. And the reason is that like deterministic algorithms, since these have to have like worst case guarantees for every single input, they have to be like pretty pessimistic. I'm going to misspell this word, but it's fine. They have to be pretty pessimistic, right? Randomized algorithms, however, these can be more optimistic. And specifically what they can do is they can like exploit nice properties about the problem that they're solving. Right, so in some sense, like randomized algorithms are allowed to be more optimistic than deterministic algorithms. And there's like many examples in practice of something of the following. Like either we have like a polytime algo, but it's randomized. And like there's no known deterministic algorithm. Another thing that happens is sometimes we have like, there's no known polytime. Note that you can always like determinize a randomized algorithm. There's no known polytime deterministic algorithm. And then you also have like, I don't know, sometimes there's like polytime algo that's random. And there's also, let me write this a little bit better. And there's also a polytime deterministic algorithm, right? But the rando one is much faster. Two like examples of this are like, maybe you've seen this before, but like two big examples of this are like primality checking, right? Checking whether a number is prime. You can do it deterministically in polytime, but it's pretty like horribly inefficient in practice. But the randomized version is pretty. Let's move on. So I want to give you a bad example of like a definition for like randomized algorithms, right? Let's say that like 99% of people in the world don't have a disease, right? And I want some kind of like disease testing kit, right? Right? Then how do you feel about like this algorithm? Algo, it takes in some sample and it says, no, this sample doesn't appear to, I don't know what the correct word is but like be positive. Right, so like how do you feel about like this kind of randomized algorithm where just like I take in a sample and be like, nope, this person didn't have the disease, right? Like 99% of the time it's correct, right? Yeah, you're right, it's not random. Maybe flip a coin and then say, no, this algorithm doesn't appear to be positive, or something to that effect, right? Like the point being that like this algorithm where it's kind of like, I'm usually correct, it's not very useful, right? So here's the thing, right? Like maybe this is a kind of a facetious example, but like randomness is like usually like in 251, we don't want it to come from your inputs, right? Specifically, it's like, it's hard to know anything about the distribution of your inputs. And this is like, maybe I should say usually hard to know. Usually, well, I'm really bad at writing on an iPad, right? Like the distribution of your inputs you're actually going to run your algorithm on, right? There's some exceptions, right? Like for instance, like cryptography, where like usually your like inputs are coming from some random like distribution. But like usually you don't want to really make so many assumptions that like, oh, most of my inputs are going to be like, if I pick the first thing as a pivot, it probably won't be that bad for quick select or something like that. We don't want to like make those random like weird assumptions about like the inputs that we're going to be running on. Cool. So this leads us to like kind of two better types of randomized algorithms that we usually use in 251. And the two types are like Monte Carlo and Las Vegas, right? So let's quickly like remind you the difference. Monte Carlo, this gambles with correctness and has some guaranteed runtime. And Las Vegas, this gambles with runtime but if it gives you an output, it's definitely correct. And there's a really nice mnemonic that we can remember. And since this is like being recorded and going to be YouTube, I should probably make a disclaimer. This is just a joke. But there's a nice mnemonic that we can use to remember like which algorithm is which. And Las Vegas is in America, and America is always right. Cool. So if you kind of forget like which one is Monte Carlo and which one's Las Vegas, remember that America is always right. So if it gives you an output, it'll be correct. If Las Vegas gives you an output, it'll be correct. Cool. And then, okay, now I think we're going to get more into the content. That was some of the motivation, but let's get a little bit into the content. I'm not giving you like the fully fleshed definitions for Monte Carlo and Las Vegas because you have that on Diderot. But I do want to make a couple of comments about like how you can kind of go back and forth between like Monte Carlo and Las Vegas algorithms, because it's not kind of as simple as we've made it out to seem, right? To go from like a Las Vegas to a Monte Carlo algorithm, right? This one isn't too bad, right? We have an algorithm that's always correct, but it has some like expected runtime. It doesn't have like a guaranteed runtime. So what can we do to make it have like a guaranteed runtime that's close to its expectation? We can just kind of like stop the algorithm at some point. If the algo is taking too long, just stop and return error. Okay, and then if we want to go from like a Monte Carlo algorithm to a Las Vegas algorithm, right, then kind of the idea is that like every time we run, we'll definitely run like within some amount of time, but there's like some small probability of error, right? So the idea is kind of like run the algorithm over and over until your output is correct. Now there's like an assumption here, right? There's a really important assumption here, and that's that like you have some way of telling whether your like output is correct. Like the assumption is that you can kind of quickly determine whether your output is correct. Okay, cool. So yeah, if you have a way of telling like whether the Monte Carlo's algorithm's like output is correct, then cool. If you don't, maybe it's a little bit more complicated to go from like Monte Carlo to a Las Vegas algorithm. Cool. So let's talk about probably the reason why a lot of you are here, the min cut problem, right? So the min cut problem is a difficult problem. We have a randomized algorithm for the min cut problem, a Monte Carlo algorithm that runs in poly time and has a pretty decent like error probability. So let's talk about how that actually works. Before we do that, let's talk about what the min cut problem really is. So essentially it's like you're given a graph, G equals VE, and what you want to do, this is your input, and this is your goal, it's to like kind of partition the vertices into two buckets, right? So kind of like give every vertex a color, like either red or blue, and minimize the number of edges that are cut edges, aka edges that kind of like go from one red vertex to one blue vertex. Right, so this is our goal, right? This is kind of similar to max cut, where we try and maximize those number of edges, but this is the opposite, right? Like we're trying to minimize the number of cut edges, right? So we're trying to find the best cut. Cool. So this problem is actually pretty hard to solve, but we have a pretty good Monte Carlo algorithm for it, which means that it'll have a guaranteed like runtime, but it'll gamble a little bit with correctness. So before we can talk about that algorithm, we need to kind of discuss like what a multigraph is. And multigraph, just like in short, is like you can have multiple edges between two vertices. So for instance, a picture like this is okay. Cool. So now let's talk about like kind of how the min cut algorithm actually works from lecture, because I do agree that it is very complicated and it is similar to something on your homework. So let's give that, let's talk about that a little bit, right? So basically the algorithm, what we're gonna do is we're gonna do kind of two things. First, we're gonna kind of come up with some like initial randomized algorithm that manages to find like a min cut with like 1 over polynomial like probability success, right? Like greater than or equal to 1 over some polynomial, right? And then we can boost it and make that error probability kind of like arbitrarily close to 0, right? So maybe that doesn't make much sense right now, but Hopefully when we get into the details, it'll be a little bit clearer. Cool. So our goal is to come up with a Monte Carlo algorithm that runs in polytime with error probability. Let's say I think we need it less than or equal to 1 over e to the n. Okay, so our goal is to come up with a polytime Monte Carlo algorithm that has error probability less than or equal to e to the n. So there's going to be 2 steps to this. The first step is like we're going to come up with an algorithm with error probability, right? At most 1 over n squared. And then the second step is we're going to boost success probability, success probability, at least 1 over n squared. And then we're going to boost this success probability to greater than or equal to 1 minus 1 over e to the n by running multiple times. So another kind of caveat comes up now when we're talking about like Monte Carlo algorithms and how they really work, or like boosting in general, I suppose. And that is that, like, earlier I said that if you wanted to kind of like make a Monte Carlo algorithm into a Las Vegas algorithm, you could just keep running it until the output is correct. Here in MinCut, when we try and do this boosting eventually, it's not going to be clear when our answer is correct, right? Like we might get a cut of size 5, a cut of size 10, a cut of size 7. We'll get a bunch of different size cuts potentially, right? And it's not very clear like if any of them are correct. But if one of them were to be correct, it would probably be the smallest cut amongst all the ones that we found, right? Cool. So there is still some kind of reasonable way to take all of those outputs and determine which is like the output that makes the most sense to give out. Cool. So yeah, we need to kind of come up with a way to do this first step. And then once we do that, we need to learn how to use that first step as a black box to boost the success probability. And the key insight here is that like if we were able to get our success probability in polytime to 1 over some polynomial amount, then we're able to do this kind of like nice boosting where we can make our error like 1 over some exponential. Cool. And still be in polytime. It'll make sense why that's the case when we do part 2, but just know that like the result from part 1, where we have a polytime algorithm with 1 over like poly as a success probability, is actually really good for starting out. Cool. So here's the algorithm, right? The algorithm, and I won't give you the formal algorithm, I'll just tell you what it does. Is essentially you have like a bunch of vertices and you have a bunch of edges, you have your original graph, right? And then basically it just kind of chooses an edge at random. Maybe I should learn how to use color. It chooses an edge at random and it contracts that edge. Oh, struggling with technology. Contracts that edge into one super like vertex. And that kind of corresponds to like saying that they're going to be in the same bucket eventually in the final solution. Does this make sense? Right? Kind of like how when I contracted that edge, I got to this new picture. Cool. So the algorithm is you're going to keep contracting like edges in your graph, right? Until you eventually end up with a graph that kind of has just 2 vertices left, 2 super vertices, if you will, right? Maybe we get like A, B, E, and you get like C, D, right? So that corresponds to like this cut. And yeah, thanks. I forgot the DE edge. Cool. Yeah, so this corresponds to like this cut. Do I have enough cut edges here? No, I should have one more. Cool. So yeah, so this is our algorithm. We basically just start with a graph on n vertices, and then we keep like reducing a vertex by contracting an edge. And then the edges that we keep are kind of the edges that are not like internal, right? So like if we contract the edges from the one between A and B, then like all the edges between A and B kind of get compressed into one. And the edges that we keep are only the kind of external edges, right? So at the end, all of our external edges are all of our cut edges, right? So this here corresponds to a cut in the original graph. does the algorithm make sense? So basically what the algorithm is doing is it's guessing a cut, and we're going to prove that the cut that it guesses by just kind of choosing an edge at random to contract actually is not a bad cut. Like there's a 1 over n squared probability or greater that we've outputted a minimal cut by doing this process. Does anyone have any questions about the algorithm itself? So the original graph has 3 cuts. So the original graph has more than 3 cuts per se, but this was just an example of how the algorithm could have run if I just kept like contracting edges and eventually get down to like kind of these 2 super vertices. If I were to have chosen the cut that looks like this, sorry, let's take a color, I don't know, green. If I chose the cut that looks like this, right, and I made this like my cut, and then I made this my other cut, then see that the number of edges between S and V minus S, there's 3 of them, right? So it's not, yeah, so does that make sense where the 3 comes from? Cool, cool, awesome, thanks for asking. Cool, so we got this. And now what we need to do is we need to kind of prove that this like algorithm, which seems kind of silly, actually does something useful, right? So let's see why that's the case. Cool. So what we're going to show that this algorithm, so if you're given a graph, right, there could be multiple like best cuts out there, right? But we can think in our head, like just once you're given a graph, you can kind of think in your head, there might be multiple like best cuts out there, but think about one very specific best cut in your head and kind of like fix that in your mind. And we're gonna like kind of compute the probability that not only does like this algorithm find a best min cut, but it finds like that specific like best min cut in the one that you've been thinking about in your mind, right? That's maybe a weird way to explain it. Let's go with this. So given a graph G, right, there could be multiple best min cuts out there, right? Let's say that like S1, S2, dot, 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 S like, I don't know, let's give it a weird letter, R, are like R min cuts, right? See, these are like R ways to kind of like partition the vertices, R different ways to partition the vertices that kind of like give you a minimum number of cut edges, right? Now each of them kind of correspond to a set of like, a set of kind of edges that become cut edges, right? And they're all equal to the minimum possible number of cut edges. Does this picture make sense? Right, so there might be like multiple best min cuts out there, and they all kind of correspond to like a different set of edges that become cut edges, right? But each of these like different sets have like the same number of cut edges, and specifically like the minimum possible for any way to have cut up the graph, right? Now what we can do is we can kind of like think of a specific one. Like let's think of like S1 and F1, for instance. Let's think about like this solution. Some optimum solution. So we care about the probability that our algorithm finds one of these solutions, right? That's going to be bigger than or equal to probability that algo finds one of these solutions is going to be bigger than or equal to the probability that the algo finds this solution. S1, F1. Cool. So we'll show that this probability here is bigger than or equal to 1 over n squared. Well, specifically what we're going to show is that this is bigger than or equal to 1 over n choose 2, which is bigger than or equal to 1 over n squared. Cool. So let's think we fixed an F1 in our head, an S1 in our head, and we're going to show that the probability that we find that specific cut is at least 1 over n squared. Okay, so how do we do this, right? So we need to make a couple of observations. We need to make a couple of observations first, right? So the first observation that we've already made is that like for any I, a cut in GI, right, of size k corresponds to a cut in the original graph G of size k. Now maybe I should have told you what GI is, right? So this was our original graph here, right? you can call this like G0. What I mean by G0 is it's the graph G, but like kind of 0 vertices have kind of like been destroyed. This graph here would be G1 because I kind of like destroyed B and put it into A as a sense, right? That's kind of a weird way of thinking about it. You can also think about it as like GI is like what the graph looks like after the ith iteration of the algorithm, right? And then here we'd have G n minus 2. Notice that the algorithm will always have n minus 2 iterations because it starts with n vertices. On every step, it destroys a vertex kind of, and it only stops when you have 2 vertices left. So any kind of cut in an intermediate graph of size k also corresponds to a cut in like the original graph of size k. Like for instance, if you look at G1 and if we look at a cut here like ABE, right? The cut edges are going to be exactly the same as the cut edges in the original graph, G0. Cool. Right, so that's one observation. Another observation is the following, right? Specifically this other observation, let's call it 1, call it 2, is that like a specific cut is always going to be bigger than or equal to in value than the min cut, right? So what I mean by that is kind of like for any like VI, for any vertex B in GI, right? The cut that's just like V and the rest of GI has like at least as many cut edges as the minimum cut in G, right? Because like the cut that's just like V, which could be a super vertex, and the rest of the graph GI, right? That corresponds to a very specific cut in the original graph G, right? So a specific cut is always going to be bigger than or equal to the min cut in terms of the number of cut edges. Okay, cool. So these are two like very important observations that we're going to use, right? So now how can we talk about the probability that our algorithm finds F1, right? We can think about the probability that we output this specific cut is the same as the probability that we never kind of contract one of the cut edges. So this is going to be equal to the probability that the algorithm never contracts an edge in F. Cool. Are there any questions so far about anything that I've said? I think this is a good point to check in. Como, anything on your side?
Nope, nobody's asked anything.
Cool. All right. So the probability that our algorithm finds F1 is going to be equal to the probability that our algorithm never contracts an edge in F at all. Okay. So that's going to be the same as like the probability that our algorithm does not contract an edge on some first iteration, does not contract an edge on the second iteration, and does not contract an edge in F on the last iteration, where EI denotes the event that the algorithm kind of contracted an edge in F on the ith iteration. Cool. So the probability that our algorithm never contracts an edge in F is the probability that it didn't contract one on the first iteration and not the second iteration and not on the last iteration, right? Cool. And then this is equal to, right, just by like kind of the chain rule, the following. E2 given, not E1, dot, 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 probability like E n minus 2 given like E1, dot, 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 E bar n minus 3. Cool, right? And this is because our algorithm has n minus 2 iterations, always. Cool beats. Right. Maybe there's one small silly thing that I forgot to mention. It's that like the cut has to be kind of like at least of size 1, right? You can't say like, oh, I'll make all the vertices blue. That way there'll never be a blue-red edge, right? That's not allowed. Cool. So we have this, right? So now we want to analyze this. So like, let's analyze the probability of E1 bar, right? So what's the probability that we don't contract an edge, right, in F, right? Well, we know that the probability that we do contract an edge in F is going to be equal to the size of F over the number of edges, right? Because we choose an edge to contract uniformly at random, right? And then there are these many edges, size of F edges that we don't want to contract. So we have this, right? Now this is great. This is totally fine, but there's one issue with this, right? this doesn't really generalize that well. Sure, I can analyze probability of E1 right now, but how am I going to analyze probability of E2 or probability of E3, etc., given like not E1, right? It's going to become really complicated because on the first iteration, I know that I have like m edges in my graph, right? But on like successive iterations, it's kind of difficult to tell how many edges I still have in my graph because some of them might have disappeared, right? Any of the internal edges that I contracted, right, have kind of disappeared from my graph. So I don't know how much m will decrease on like the second iteration or the third iteration, etc. I do know on every iteration that I'll decrease my number of vertices by 1, but again, I don't know how the number of edges are going to change. So it would be nice, instead of having this being like some probability in terms of like the number of edges in the graph, as being some probability as in terms of the number of vertices in the graph, right? So we'd like to have this in terms of the number of vertices, because we know how this changes. Cool. So how can we figure out like an expression related to like the number of vertices in the graph relating to the number of edges in the graph? Well, we can use handshake lemma, right? We know that 2m is going to be equal to the sum of v and v of degree v, right? And now the degree of a vertex, right? The degree of a vertex, this is the size of the cut v and everything else. Make v red and everything else blue, right? So the degree of a vertex, right, is an upper bound on the min cut, right? So we know that each of these terms, oh, what did I do? Sorry, guys. Each of these terms, right, there's like n things in the sum. And then each of these terms is going to be at least the size of f. Cool. So then we can rearrange this expression to m is greater than or equal to n times the size of f, right? And we can get what? We can get the size of f, right, over m is less than or equal to, right? Where is this? 2 over n. Cool. So we have that the probability of E1, right, is less than or equal to 2 over n. And this implies that the probability of E1 bar is greater than or equal to n minus 2 over n. Cool. So that's awesome, right? Now, how can we analyze probability of EI, right? When I change this to EI, what changes here, right? M is now like the number of edges in the graph GI, right? And then the number of things in this sum, right, is going to be n minus I, not n, right? Because I've lost kind of I vertices at this point. Does that make sense? Or I guess technically like n plus 1 minus I, because I didn't zero index here, but whatever. Does that make sense? So like in general, we'll have that like probability of like E1 bar is equal to like n minus 2 over n. Probability of like E2 bar given E1 bar is going to be like n minus 3 over n minus 1. Or no, what am I saying? Is that right? Yeah, n minus 3 over n minus 1, right? Because I'll get something like here I'll get less than or equal to 2 over n minus 1, which means that this part will be n minus 3 over n minus 1, right? And so on and so forth. Cool. So this means that like the probability that like my algorithm finds f is going to be greater than or equal to this large telescoping thing, n minus 2 over n minus 3 over n minus 1, dot, 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 and then eventually, right, I will have here at the bottom, what do I have at the bottom? I guess I have 2 at the bottom. What? No, and why am I blanking right now? 1 over 3, I think. Yeah, I'll have this, right? And then this all cancels out and gives me 1 times 2 over n times n minus 1, which is equal to 1 over n choose 2, as desired. Cool. So yeah, so we have this exact expression that we wanted, right? We showed that the probability that our algorithm finds a specific solution that we fixed in our head is at least 1 over n choose 2. Cool. So let's talk about the second phase now. But before we do that, I want to pause for a question. Does everyone understand how we were able to kind of prove that this algorithm finds like a specific min cut with probability at least 1 over n squared? Was there any part of this that was unclear? Cool. I guess I'll move on to boosting then. Right, so now we have an algorithm, right, that in polytime, I didn't justify the polytimeness, but that should be clear, that in polytime kind of like outputs a min cut with probability at least 1 over n squared. So now, if I run this algorithm t times, right, and I take output like the smallest cut that I see, right, then what's my probability of error, right? Right, so my probability of error is that like, if I ran this algorithm t times and I output the smallest cut I see, the only way I can be wrong is if I never saw the min cut, right? If I saw the min cut at some point, then I'm going to output the min cut, right? So my probability of error is like probability that I was wrong t times out of t, right? So if I let AI denote the event that I'm wrong the ith time, then my probability of error is equal to this. I apologize. The probability of error is the probability that I'm wrong every single time. So it should just be this, right? Just the probability of A1 intersect A2 intersect AN, right? And notice that these are all independent. So it's equal to the probability of like A1 times the probability of A2 dot 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 times the probability of like AT, right? And this is the same thing as like the probability of A1 to the T, right? Since my probability of error is going to be less than or equal to, right, 1 minus 1 over n squared, this makes this whole thing less than or equal to 1 minus 1 over n squared to the t, right? So now I can use this like kind of nice fact that for all x in the real numbers, 1 plus x is less than or equal to e to the x, right? What does this mean? If I take x equal to like minus 1 over n squared, right, I have that like 1 minus 1 over n squared, right, is less than or equal to e to the minus 1 over n squared. Now, if I throw a t onto this, I can put that t up here, right? So if I take t to be something like n cubed, that this is equal to e to the minus n cubed over n squared, which equals to 1 over e to the n. Cool. So what did I do? Yeah, I said that if I run this algorithm t times, specifically n cubed times, which is a polynomial number, right, then the probability that like I'm wrong every single time is at most 1 over e to the n, right? Which means that the probability that I find like the correct answer is pretty high, like at least once is pretty high. So this boosting actually really helps us. So we managed to take a success probability of like 1 over n squared and boost it to like 1 minus 1 over e to the n, which is amazing. Cool. Does anyone have any questions about this? How did I decide an optimal t? Is there a threshold? Right, so I'm addressing Scott's question in the chat, right? The reason I chose this t, right, is because I wanted my algorithm to have an error probability that's at most 1 over e to the n, right? So I chose a t that made sure that my like error probability bound would be at most 1 over e to the n. So I can't really choose that t until I'm literally like down here. Once I've gotten to here, I'm just like, hey, which t would make my error probability 1 over e to the n? Cool. So let's talk about boosting in more generality. So boosting when you have like a one-sided error versus a two-sided error. Because like I said, it's not very clear like how boosting always works, right? Like if you have like a way to tell whether your output is correct, then it's pretty easy. But what if you don't have a way to tell? What if it's just like a decision problem, right? So maybe I'm giving away the answer to one of the check your understandings, but like if you're trying to do this kind of like process with like a decision problem, you can't assume that like once you output 0 or 1, you're able to tell whether that 0 or 1 was correct, right? If you had a way to check whether like the instance should have been 0 or the instance should have been 1, why were you using a randomized algorithm in the first place, right? But cool, let's talk about like decision problems and boosting. Right, and the key idea here is that like usually what you'll do is you like run it a lot and take the majority answer. For one-sided error, there's going to be a little bit different, right? If you like know that your algorithm has a one-sided error, then you can do something like a little bit more intelligent than that, actually, right? So let's say that like you have a decision problem, right? And you have an algorithm A, and if X is a yes instance, right, then that means that like A of X equals 1 with like 100% probability, right? And if X is a no instance, right, then that means that like A of X equals no with like probability greater than 50%. Cool. So now if we run like X on this algorithm, right, if you see yes, like here, maybe let me ask like kind of like a small trick question, right? Like if I take an X and I see the algorithm say yes and then say no. So this is my first question, this is my second question. If I see the algorithm say yes, do I know that X is yes? And do I know that X is no? So let's do like a little bit of like a poll just for interactivity's sake, right? For the first question, right? Like I take an X and I run A of X, right? And A of X equals yes, A of X equals no. So if A of X equals yes, do I know X is yes? Cool, cool, cool. All right, so those of you who voted have said no, and that's completely correct, right? If A of X is yes, I don't know that X is yes. What about the other question? If A of X says no, do I know that X is no? All right, now you guys are all saying yes. Cool. Yeah, I see a lot of yeses, right? So our algorithm can be this, or like our new algorithm for boosting. Run a bunch of times. If it ever says no, right, then output no. Otherwise, output yes. Right, so just keep running A. If you ever see a no, then just stop, output no. But if you keep saying yes, 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 then eventually output yes, right? And now what's like the error probability of this, right? Like it's at most 1/2 to the n, right? If I run this like a bunch of times and I make this like a bunch of times n times, right? Then the error probability for any input, right? A yes input or a no input, right? Like we don't talk about like, oh, it's good for some inputs. No, randomized algorithms have to have guarantees for all inputs. The error probability is at most, right, 1/2 to the n, right? Like if you were a no input, right? If you were a yes input, then you couldn't have tricked my algorithm, right? But if you were a no input, the only way you tricked my algorithm is you said yes like n times. And that happens with probability less than 1/2 times 1/2 times 1/2 times 1/2 n times. Cool. So this is like boosting with a one-sided error, right? Let's talk about boosting with a two-sided error. And let's say that I have an algorithm, like X is an instance. And the probability that like, let's say A of X is not equal to like F of X, and this is like the true answer, is going to be like less than or equal to 1/4. Right now, once an algorithm with success probability, or we can say, let's say error probability is less than or equal to 1/2 to the n. Cool. So the idea here again is not that we just run it a bunch of times and like if we ever get the right answer, just output the right answer. Because again, we don't know whether 1 or 0 is the right answer, right? For these kind of like computational problems, maybe it makes more sense, like you know what the right answer is or what the best of your answers are. But here it's a decision problem. So the best thing that we can do is we can just run it a bunch of times and then take the majority answer, right? So let's say that we run it like, I guess I'm giving away like the magical number, but let's say, oh, it says this in the question. We run A of X 6n times and then output the majority answer. Right, and now like if we to analyze like the probability of error, we need to like analyze the probability that we were wrong like more than 3n times. What's the probability we are wrong at least 3n times? Right, so we can do this kind of like with some random variables, which will maybe be nice probability review. Right, we can take like x, and we can say that x is equal to x1 plus dot 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 plus x is 6n. And this is going to be a random variable for a number of times we're wrong. So like fix some input string x in your head, right? This is the probability, this is the number of times that we're wrong. This is like indicator variable if we're wrong on the first try, right? And then similar here, right? Now, we care about like the probability that like x is less than or equal to 3n, right? Cool. So the probability of error, right, is a probability of error is actually a typo, is a less than or equal to the probability that x is greater than or equal to 3n. Cool. So what is this probability that x is at least that, right? It's equal to like how many ways can like x be greater than or equal to 3n, right? It can either be like 3n plus 1, 3n plus 2, all the way to 6n, right? So we case on like all of those possibilities. Maybe I can change this a little bit. Let's make this a number of times that we're right, just because it makes the math a little bit nicer, right? And then this becomes a probability less than or equal to 3n, right? So the number of times that we can be right is like somewhere between 0 and 3n. So it's all the ways that we can be right, like k times. And that's something like this. I equals 0 to 3n, right? The probability that x is equal to I, right? So the probability of error is like the probability that we were right 0 times plus the probability we were right 1 time plus etc. So then how do I like simplify this expression, right? This is equal to just like by coin flipping 6n choose I. So this is kind of like choosing the I times that I was going to be correct, right? And I'm correct with probability 3/4 of the I, and I'm wrong with probability 1/4. Cool. And then this just simplifies really nicely to 27 over n to the 64 to the n, which is less than or equal to 1/2 to the n, right? So I'm not going to really do the math, but the point here was that like, hey, if we just kind of take the majority answer, then we're going to actually get a pretty good error bound. There's maybe one more kind of point that I want to talk about. And another point is that what happens in max cut, right? If you kind of randomly contract two vertices instead of an edge. So what happens in max cut if you randomly contract two vertices instead of randomly contracting? Who thinks that this would still be a good algorithm? Does anyone have any like thoughts as to whether this would be good or bad? It is what contracting an edge does though, but like in the past, we would never contract, like if this was our graph, this guy and this guy would never get contracted together. So the same contraction where we kind of destroy like all the internal edges between them. But now like maybe I can contract like two vertices that maybe don't even have an edge shared. Is this a good algorithm or a bad algorithm? So this algorithm is kind of like similar to just kind of guessing a max cut by just guessing like a random partition, right? I'm not going to make the claim because it's wrong that like every partition has an equal chance of being like picked. But there are plenty of examples of graphs where like there's exactly one min cut, right? And the probability that you would just kind of guess that min cut by like this procedure is very low. Like if you think about what this is really doing, it's really just being like, hey, you two are going to be the same color. Now you're going to be the same color as that guy. You're going to be the same color as that guy. You're going to be the same color as that guy, etc. Right? It's really just like lining up your vertices v1 up to vn, and then you have like a red team and you have a blue team, right? And then you kind of start with being like, okay, v1 you're red, let's say. Now v2, it's just kind of like a weird way of choosing like which vertices are red and which vertices are blue, but it doesn't really have anything to do with like the edges in the graph. And if it has nothing to do with the edges in the graph, it's basically pretty much just guessing a partition, right? So this actually isn't really great. Cool. And an example of that is like you can have like kind of like a clique over here connected with one edge to like a clique over here, right? And so there's only one good kind of cut in this graph. And that's specifically this cut, right? And the probability that you'd find this cut with this kind of an algorithm is like exponentially small.